of experiments were conducted at the UL test facilities in Northbrook, Illinois, and at the Delaware County Emergency Services Training Center in Sharon Hill, Pennsylvania, to identify and quantify the electrical shock hazard posed by photovoltaic equipment during fireground operations. These experiments provided the scientific basis for the safety considerations presented here. These considerations apply to the types of PV systems used in these experiments. You should be familiar with the systems in your response area and understand the similarities and differences. Since this research has been conducted, improvements have been made with codes and standards so that firefighters are performing their standard operations as safely as possible. These improvements have included improvements in terminology and function of the rapid shutdown, which is now known as PV hazard control. The PV rapid shutdown system was the first means to reduce firefighter hazards for firefighters that need to fight fires on buildings with PV arrays. Due to the differences in adoption of NEC codes, it's imperative that firefighters know which version of the code is being utilized within their state or municipality. Click on each year to learn more. This system is intended to be used by firefighters to reduce hazards of working around an electrically live PV array and its wiring. This article is intended to establish a safe perimeter around the PV array via functions such as an output disconnect or a function that attenuates or limits PV array output power to a low level. The 2017 NEC revision included new requirements for rapid shutdown protection internal to the PV array. The 2020 NEC is very similar to the 2017 NEC, but required a listed PV hazard control system instead of a PV rapid shutdown array for protection inside the PV array boundary. NEC 2020 aligns directly with UL Standard 3741, the standard for safety for photovoltaic hazard control, which was published in December of 2020. Click here to learn more about UL 3741. The focus of UL 3741 was to better define the specific hazards firefighters are exposed to and how to evaluate the hazard protection to increase firefighter safety. While PV rapid shutdown requirements and equipment focused only on electronic solutions to control or limit voltage that could cause a risk of electric shock, PV hazard control focused more specifically on keeping adult firefighters out of a hazard current path while they were performing their firefighting job on a building with a PV array. Where PV rapid shutdown assumed a hazard and required a specific electronic solution, PV hazard control takes a holistic approach to evaluate a complete PV array to reduce hazards for firefighters. As discussed, the NEC and UL 3741 have already been aligned, and the published NEC 2020 replaces the reference to a listed PV rapid shutdown array with a listed PV hazard control system. UL 3741 listed PV hazard control systems will provide authorities having jurisdiction with the easiest means to determine compliance with the NEC. The National Electrical Code, or NEC, requires a means to disconnect the DC wiring of the PV system from all other circuits in the building. This device must be located at a readily accessible location on the outside of the building or inside nearest the point of entrance of the DC wiring and appropriately labeled. In addition, a method must be provided to disconnect equipment such as inverters and charge controllers from all ungrounded conductors. Keep in mind, when the required PV system disconnects are opened, The conductors between the PV modules and the disconnects can remain energized when the PV modules are illuminated. This presents an electric shock hazard to firefighters who may come in contact with energized wires and PV modules. In this illustration, a residential two-story home has a PV system installed on the roof of the home and garage. It consists of a single array comprised of 3 separate strings. All circuits are energized, so all the system wiring is red to represent live circuits. Currently, all switches are on with the handles in the up position. Click to view each component. The following is an example of a residential de-energizing sequence. When the AC disconnect switch to the inverter is turned off, the inverter subsequently turns off and a part of the circuit is de-energized. The switch handle is now in the down position and the wire is green to indicate a de-energized circuit. The main circuit breaker has been turned off and cuts all power to the AC disconnect switch. The utility service has been disconnected. This interrupts the AC power to the home. DC disconnect switch 1 has been turned off and there is no change to the energized circuits. DC disconnect switch 2 is turned off and the circuits remained energized. All 3 DC disconnects have been turned off with no immediate change to the energized circuits. Unless otherwise marked on the inverter, within 5 minutes, the indicated circuits will bleed down to below 30 volts. With all 3 DC disconnects turned off, the indicated circuits are beginning to bleed down. The indicated circuits have now bled down to a safe level. An appropriate tarp was placed on the garage PV string to bring the voltage in that string to a safe level. The use of tarps is discussed later in this course. A second tarp can be added to bring more of the PV system to a safe voltage level. Only when all 3 strings are tarped will the entire PV system be at a safe voltage level. Be aware that if any tarps are deployed to de-energize any part of the array, all DC disconnects must be open. This illustrates the potential to create a backfeed due to the partial shading of the array with one tarp in position and DC disconnects closed. The covered string will consume the energy produced by the balance of the array, potentially increasing its temperature and creating an additional fire hazard. No 2 incidents are the same, and not every scenario involving a PV system will have the same solution. Even in these controlled experiments, with the same experimental test system and fuel load, there were differences in how the fire impacted the PV system. The potential electrical hazard and the most appropriate means to mitigate that hazard will vary from one incident to the next. As a result, these considerations are just that, considerations. These are factors that should be considered in concert with your response capabilities and resources to improve the effectiveness and safety of your fireground operations. Use this menu to begin exploring the safety considerations. Standard operating procedures generally require that the electrical power to a building be disconnected before fire suppression activities begin in order to reduce the risk of electrical shock. The standard process of isolation from utility-supplied power is inadequate when the building is equipped with a photovoltaic system. Turning off the PV system disconnect will de-energize the DC power on the load side of the disconnect, for example, the inverter. However, the electrical wiring and other system components between the PV modules and the disconnect can remain energized if there is sufficient light energizing the PV array. Although photovoltaic systems are designed and intended to be exposed to wet conditions, the hazard posed by direct water application from a fire department hose stream was previously unknown. Photovoltaic systems installed after 2014 following the National Electrical Code, or NEC, will include rapid shutdown systems that have an actuator switch and signage near the building's electrical service entrance. A firefighter can de-energize photovoltaic circuits 3 feet outside the perimeter of the photovoltaic array. The 3-foot perimeter around the PV array will allow a firefighter to perform ventilation work without contacting energized circuits. These experiments were conducted to investigate the potential shock hazard from the direct impact of fire department hose streams. In each experiment, the current produced in the circuit, through the hose stream, and back to the nozzle was measured under various nozzle type, water pressure, and distance. Click to learn. These experiments were conducted to investigate the potential shock hazard from the direct impact of fire department hose streams. Click to learn more. 2 different nozzles were used for these experiments, a smoothbore and an adjustable nozzle. Click the information icon to learn more, or click the X to return to the menu. The main water supply for these experiments was pond water from Lake Wellborn at UL's campus in Northbrook, Illinois. However, experiments were also conducted with salt water and a foam water mixture. Click to see the conductivity of the different water sources. The voltage source for these experiments was a DC power supply adjustable from 0 to 1,000 volts. Click the icon to learn more. Each experiment placed the target plate a fixed distance from the nozzle. A particular nozzle type and water pressure were selected. With the nozzle spray aimed at the target, the power supply was turned on at 1,000 volts DC. Data collection began, and the voltage was gradually lowered from 1,000 volts DC to 50 volts DC, dwelling for seconds at the fixed voltages of 1,000, 600, 300, and 50. Use this menu to explore the results, or click Next to move to the summary of the findings. In these experiments, the distance from the nozzle to the copper target was reduced to 5 feet to represent the dousing of PV components during overhaul operations. The water pressure was also reduced to provide a constant and reasonable stream to the nearby target plate. The first experiments were conducted with the smoothbore nozzles at a distance of 10 feet between the nozzle and the copper target. The water pressure was adjusted such that a constant solid stream was provided from the nozzle to the target. This resulted in water pressures of 21 psi for the 1-inch diameter nozzle. Tests were also conducted at 35 psi. These experiments were conducted with the smoothbore nozzle at a distance of 10 feet. The water pressure was adjusted such that a constant solid stream was provided from the nozzle to the target. This resulted in water pressures of 14 psi for the 1.125" diameter nozzle. These experiments were conducted with a smoothbore nozzle at a distance of 10 feet. The water pressure was adjusted such that a constant solid stream was provided from the nozzle to the target. This resulted in water pressures of 10 psi for the 1.25" nozzle diameter. Similar experiments were conducted with the adjustable nozzle with a full stream from a distance of 10 feet. As the nozzle was adjusted down from the full stream towards fog, the leakage current quickly dropped to near zero. The distance was increased to 15 feet in these experiments while using the 1-inch smoothbore and the adjustable nozzle at full stream. In these experiments, the distance between the hose stream and the target increased to 20 feet. Each experiment placed the target plate a fixed distance from the nozzle. The distance was increased to 15 feet in these experiments. In these experiments, the distance between the hose stream and the target increased to 20 feet. Using the 1-inch smoothbore nozzle and water pressure of 23 psi, a maximum of 1.5 milliamps was measured at 1,000 volts DC. The water pressure was then increased to 60 psi, and the maximum current at 1,000 volts DC remained less than 1.5 milliamps. A similar experiment was conducted with the 1.25" smoothbore nozzle at 29 psi, and the maximum current at 1,000 volts DC remained less than 1.5 milliamp. Because 1.5 milliamp was considered a safe current level, no further testing was conducted beyond a distance of 20 feet. Additional experiments were conducted with different water sources. Click to see the results. Experiments were conducted with a Class A foam in concentrations of 0.5% and 1%. The testing conducted used the adjustable nozzle at full stream with a pressure of 35 psi. The copper target plate was placed 10 feet from the nozzle at a horizontal orientation. For comparison purposes, the results of similar experiments with pond water are also shown. Because the Class A foam did not produce the appreciable difference in test results versus the previous experiments with pond water, no further testing with foam was conducted. Testing similar to that described above was attempted using the saltwater solution. However, due to the high conductivity of the salt water, which was 50 times that of the pond water, standing groundwater alone was found to be sufficient for creating a high current grounding path from the live copper target plate. For safety purposes, testing with salt water was discontinued. When a hose stream is aimed at an energized electrical component, electrical current can be conducted through that water stream and subsequently conducted through a person's body coming in contact with that hose. The electrical shock hazard is dependent on voltage, water conductivity, distance, and spray pattern. A slight adjustment from a solid stream to a fog pattern reduced measured current below perceptible levels. Salt water should not be used on live electrical equipment. A distance of 20 feet was determined to reduce potential shock hazard from a 1,000-volt DC source to a level considered safe.